Let's prove identities using the principle of mathematical induction. To show that these three identities here are true using the principle of mathematical induction, we need to follow its exact steps. Many references could actually say there are only two steps. Others could also say there are three steps, but generally they are just the same. When I talk about principle of mathematical induction, step one should be in showing whether the given identity is still true when n is equal to 1. We are going to assume that n is equal to 1 and see whether the identity will still hold as true. The second step is to assume that for n equals k, the statement is still true. Now here comes the difference with that I told you earlier that other references use two, references use a three, because other references would like to add additional step here, but generally it's just part of step two. We are going to show now that when n is equal to k plus 1, the identity will still be true. So these are actually two or three steps that we need to follow when we are going to prove these identities using the principle of mathematical induction. The step number one. In step one here, we are going to assume that the identity is true when n is equal to 1. What is that in other sense? It tells us that our identity should be an identity if we are going to substitute our value of n in the right hand side of the expression being 1, and if returns to the first value here, then that would mean it's true. So to show, let us use the value of n which is equal to 1 here. This would become 1 times 1 plus 1 all over 2. Then later on, we have 1 times 2 over 2. The result is 1. Question, is this the same value as the first term here on the left hand side? The answer is yes, and as therefore we have satisfied the first step. The second step, we are going to assume that it's still true for the next numbers aside from n, which is actually now corresponds to k. So we are going to assume here the step 2 should also be true when n is equal to k. That would mean the expression here will become 1 plus 2 plus 3 plus dot 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 plus n will become k. And for the left hand side, it will become k times k plus 1 all over 2. So this is now the expression. Instead of n, we change it to k. Don't worry about the representation of n being k, because we are just going to show that it's also true for the next step, which is k plus 1. And that is actually the thing that we are going to show. After completing step 2, what is now our task? Before we could actually continue proving this identity using the principle of mathematical induction, we need to understand what we trying to show. Okay, our goal is actually this one. I'm going to have it as color blue to be specified. For us to prove this identity, we need to show that if we are going to add an expression which is k plus 1 here, and of course it's an identity, we are also going to have the same expression to be added on the right hand side. So please bear with me. The point here is we have added the same expression on both sides of equation following the unique expression for the nth term or the kth term of this expression. We are going to show that this is true. What do you mean by showing that this is true? Take note that if we are going to have another value here, let's try to change, okay? Let's try to change, okay, the value of k, change it to k plus 1. In short, we will have n. Instead of k, we'll have a k plus 1. What will happen to this right hand side? This would actually become, again, let's try to change it to k plus 1. The k here will become k plus 1. Okay. The k inside will also become k plus 1. And then we have here another plus 1. Again, only the k here becomes k plus 1. And we still have another 1 term here all over 2. Or the more simplified, you will have here k plus 1 times, if you're going to break this one, you have k, 1 plus 1 is 2 all over 2. What are these two expressions now? What we are going to show is that if this colored blue region here, specifically this right hand side, is this will this return to this green colored expression here. So again, before we proceed to the proving this one, the first step is when n is equal to 1. The next step is when n is equal to k. In short, just simply change n to k. After that, before going to step 3, we need to find out rather what we would like to prove. And what we would like to prove is if we are going to add another value on both sides of the expression having the same identity here, will this return to this right hand side of of the step 2 equation by just changing it to k plus 1. We need to show that this expression will return to this expression here. So we have here k times k plus 1 all over 2 plus the quantity k plus 1. So that's k, that's 1. Pardon. To do that, we are going to apply all necessary mathematical operations that we could think of. Well, it has a fraction, it is a rational expression here. So we could actually look for the LCD, which is 2. And 2 divided by 2 is 1 times the expression at the top. So you will have here k times k plus 1. Again, that multiply it. Plus, we all know that this may be a unit fraction with one denominator. So 2 divided by 1 is 2 times that expression. So you will have 2 times k plus 1. Next here is to factor out k plus 1. So common monomial or greatest common monomial factoring, we leave this as k, and you have here plus 2 all over 2. Now here, do we have the same expression as this assumption? And when just simply changing the value of k to k plus 1? The answer is yes. Therefore, we have proven that this identity is true for all n greater than 1. Okay, and that's it for number 1. Let's have, again, the process R. Assume that n is equal to 1. Next, let's change n to k. And before we go to the computational processes, we need to show that it is also true when we add here k plus 1 on both sides. And that should be true when if we're going to change k here to k plus 1. In short, we're just thinking about the next value in the series here. For number 2, we may have a little bit of setback here as our value here is not just n, it's now 3n minus 1. So how do we do this? Step by step. Step 1, we need to show that it's true when n is equal to 1. Again, we need to show that if we're going to substitute 1 in this expression in the right hand side, it should return to the first value here. So that being said, we'll have here 1 times 3 times 1 here plus 1. Let's use bracket. Okay. all over 2, which will follow as 1 times 3 times 1 is 3 plus 1, which is 4, all over 2. The result is 2. And this is actually the value on the first, the first term. And this is the first term of the series here on the left hand side. This would mean the first condition is already met. Second, let us try to show, sorry, that's step 2, where the expression when n is equal to k. That would mean this will become 2 plus 5 plus 8 plus dot 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 plus the n will become k. Okay. And the other side, n will also become k. K, 3k plus 1 all over 2. So we just simply substituted n for k. We need to show that if we are going to have n is equal to k plus 1, this expression here, 2 plus 5 plus 8 plus dot 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 plus 3k minus 1 plus, let's make this as k plus 1 in short, and this is where the difference comes in. Earlier, simply change it to k plus 1, but instead we have this expression here, so you have 3k plus 1 minus 1. Okay, that's what we are adding. Okay, must be the same as if we're going to change all of this to k plus 1. So you have k plus 1 times, sorry, it must be the same if we are going to add the same value here of this expression here. Let me add it here on the other side as well. Let me add the same expression on this side. So we need to show that this is also true when we add these things here. Again, why is it that earlier we only use k plus 1? Because it's just simply as k. No other terms beside it, no other expressions beside it. So we have here, we have that expression. But in here, in number 2, since it's 3n minus 1 is given, so it should stand as it is because it is actually the expression that describes all the terms here in this series. That is 1. So this is now the expression that we are going to use later in proving this identity. What we are going to prove is if we are going to change the case in this expression as k plus 1, it will become the expression k plus 1 times 3k plus 1. Okay, that's a product. Let's use this as bracket plus 1 all over 2. Or this actually k plus 1. Sorry, that's more product. I forgot. And the other side will have 3k plus 3 plus 1. You'll have here plus 4 all over 2. Let me check again. 3 times k is 3k. 3 times 1 is 3. Plus 1, you have 4. Now, should be our endpoint. And what endpoint? Our endpoint, if we are going to simplify this, this should be the endpoint. Okay, so let's show that for step 3. So you have the expression k times 3k plus 1 all over 2 plus the expression here 3 times k plus 1 minus 1 here. So let's try to combine this first. You have here 3, you will have a k times 3k plus 1, and you will have here LCD. You have 2. So plus 2 times the expression 3k plus 1, sorry, plus 1 minus 1. Okay, from here, earlier, we did not multiply it anymore since we could just simply take out the common factor here, k plus 1. However, for this expression here, there's no common factor, so instead, it will become k times 3k plus 1 plus 2 times the expression here, which is actually, that's 3k plus 4 minus 1. So you have 3k plus 3. Let us check. 3 times k, 3k. 3 times 2, 1 is 3 minus 1. Okay, I'm wrong. This is actually 2. Okay, all over 2. Earlier, in number 1, we're able to factor out the binomial k plus 1 because it's common to these pairs here. However, for this expression here, this is 3k plus 1, this is 3k plus 2, so we cannot do that. What's the next thing here is we could just simply multiply. K times 3k, you have 3k squared, k plus 1, times 1 rather, is plus k. Here, you have plus 6k, and you have here plus 4, all over 2. So more or less, this is actually 3k squared plus 7k, that's 7, plus 4, all over 2. Let's see if we could factor out this expression here. Now, 3 times 4, AC way is 12. And factors of 12 that could actually uh, be used to come up with 7 is, again, AC is 12. Factors of 12 that could become 7 is actually 3 and 4. So this expression can be factored out as 3k plus 3 times 3k plus 4. This could still be further simplified so that it will still have 3k squared. So divide by 3. This is k plus 1 times 3k plus 4. Let us check. K times 3k, 3k squared. You will have positive 3k, positive 4k. That is positive 7k. And 4 times 1 is 4. So this is actually factored out as k plus 1 and then 3k plus 3k plus 4 all over 2. Let's see if this expression here matches this expression here. Okay, let me zoom out. K plus 1, 3k plus 4, k plus 1, 3k plus 4 all over 2. So this is actually the proof that the identity for number 2 is correct. This is the answer for number 2. Before we proceed to number 3, again, very important for us to be reminded of what the steps are. Step 1, n is equal, determine if n is equal to 1 to satisfy the equation. And step 2, assign n as k. And before going to the computation processes, we are going to assume here another expression that will be added in the form of k plus 1 and add it on the other side as well. By doing that, make sure that in expressions just like in number 2, since it's stated as 3n minus 1, so it should be this expression here. This blue colored text would be our goal to show later. And what is its end point? The end point is when we go back to this expression here, and instead of k, instead of k, we are changing it to k plus 1. That's why the k here becomes k plus 1. The k here also becomes k plus 1 plus 1 still. Similar here, the k becomes k plus 1. And the k here is now k plus 1 with a factor of 3. And then later on, we have this. So once we have that expression, the green colored expression, that should be the end point of this expression here. And we apply the necessary mathematical operations. Any mathematical operations that you could think of. Let's have number 3. Number 3 has exponentiations. So it should follow exponentiation still. But of course, step 1 is still step 1. Let us determine if it's true when n is equal to 1. Again, we need to show that if we're going to substitute 1 here, it will result to this expression. That would mean you have 1 times 1 plus 1 times 2 times 1 plus 1 all over 6. Sorry. Will this become 1 squared? Let's see. You will have here 1 times, that's 2. Here, 2 times 1 is 2 plus 1, which is a 3, all over 6. So you have 6 over 6 is equal to 1, the result of 1 squared, and thus satisfied. Step 2 is now assigning n as k. Our expression here, 1 squared plus 2 squared plus 3 squared plus dot 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 plus k squared, changing n to k, must be equal to k times k plus 1 times 2k plus 1 all over 6. Okay, now let us show what needs to be proven. If we are going to have n is equal to k plus 1, it means we'll have here 1 squared plus 2 squared plus 3 squared plus dot 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 plus k squared. And now it's an exponentiation, so it will become k plus 1 squared, meaning the k here will be changed to k plus 1. Okay, and on the other side, we'll be adding the same value here to this expression. So you will have here the same expression, k plus 1 times 2k plus 1 plus 1 all over 2 all over 6 plus the same expression here. This is what we are going to show, okay? But we have added the same here. And what should be its endpoint? The endpoint is when we are going to change the case here, just like what happened here, to k plus 1. So this is actually now the k becomes k plus 1. The next value here will become k plus 1. And since we have another 1 here, looks like that. And then the k will become k plus 1 plus 1 all over 6. Or in short, in simplest forms, we'll have k plus 1 times. This is k plus 1 plus 1. In short, you have k plus 2. And then you have this expression here. 2 times k is 2 is 2k. 2 times 1 is 2 plus 1. So you have plus 3 all over 6. We need to show now that if we are going to combine these two expressions at the bottom, it should result here. So more or less the denominator is already 6. So you might be already guided with that. But still, let's continue here. This is now our step 3. We need to show that k times k plus 1 times 2k plus 1 all over 6 plus the expression k plus 1, the square of k plus 1 will result to this expression here. So let's do this by LCD again. 6. So this is still k plus 1, and then 2k plus 1 plus, we all know again, this is the denominator of 1. So 6 divided by 1 is 6 times this expression. So you will have here 6 times the square of k plus 1. Do we have something here that we could factor out, just like what happened in number 1? The answer is yes. Take note that if we say k plus 1, or the square of k plus 1 rather, there are two k plus 1s multiplied to each other. And since we also have a k plus 1 here, we could factor it out, k plus 1. And what will happen inside is you have k times this. Again, that is already been removed. So 2k plus 1 plus 6. And when we remove k plus 1, we still have another k plus 1 here since it's the square of that all over 6. Let's continue. So this is now k plus 1. Let's just simplify this because we're already there. We have shown this already. We already have k plus 1. We already have 6 here. So more or less our expression do have these two already. Let's just continue with whatever is left here inside. So you have k times 2k is 2k squared. K plus 1 is k. You have here 6k and you have here plus 6 all over 6 here. Or you have here k plus 1 times 2k squared. K plus 6k is 7k and you have here plus 6 all over 6. Let's try to factor this out. AC way. You will have 2 times 6, which is 12. Again, factors of 12 that could actually become 7 are 3 and 4. So you will have here 2k plus 3, the easy method, 2k plus 4. We could simplify this because 2k times 2k is not 2k squared, that's 4k squared. Let's divide by 2. So your factors are 2k plus 3 and that's k plus 2. These are the factors for this. So if we're going to substitute here, you have k plus 1, you have 2k plus 3 times k plus 2 all over 6. Let's see if we have the same results. This is our result here. K, the product of k plus 1, 2k plus 3, and k plus 2 all over 6. Is it the same as this? K plus 1, k plus 2, check. 2k plus 3, check. All over 6, check. We have proven this identity for number 3. It may look very confusing and very long for us. Let's just do not forget the steps. Step one, show that that the identity is true when n is equal to 1. Step two, we are going to show the expression if n is equal to k. And with that, we are going to determine what we are going to show later on as part of our proof, where we add another expression that could actually be the next to k, which is k plus 1. Okay, and before to step 3, we are going to show this blue colored text here on the right hand side specifically that it should actually be equal to this expression here by changing the values of k to k plus 1. And with that, apply necessary operations, and that's it. Please make this as part of your review. I know this is not easy for you, but just need to practice for this. Goodbye, everyone.